Hello everyone, this is Dr. V. Madhavi, Associate Professor of Chemistry, BVRIT Hyderabad College of Engineering for Women. Today, we are going to dive into the topic related to water treatment, one of the purification methods, that is ion exchange process. So what is this ion exchange process? Let us go into the detailed description. So ion exchange process, it is otherwise called as deionization or demineralization. That is, the ions present in the water. That is, it may be hardness causing salts, other any kind of ions in the form of salts. Both cations and anions can also be considered as minerals, which would be unwanted present in the water, can be removed by this method. So hardness causing salts can be removed. There are few other methods to remove hardness causing salts like lime soda process, Ullite process, but one of the most effective methods is ion exchange process. So what this method is using? Let us go into details of this. So there are ion exchangers present in the process. One is cation exchange resin, the other one is anion exchange resin. What is this resin? It is a polymer. It is an organic polymer having the bulk structure, can be used for both cation and anion exchanger processes. The resin would be same, that is, we can use styrene divinyl benzene. The same styrene divinyl benzene resin or polymer can be functionalized with acid to form cation exchange resin. The same resin can be used to functionalize with anions to form anion exchange resin. And the resin what we are going to use is highly cross-linked structure, means it would be very stabilized and strong enough so that when the purification is going on, there would be no dysfunctionalization of this resin. So we are going to use highly cross-linked resin with high molecular weight. So the styrene and divinyl benzene resin, so this would be the styrene divinyl benzene resin we will be using. When it is treated with sulfonic acid or carboxylic acid, this would be this H plus would be attached to this resin, can be now called as cation exchange resin. The same resin, when it is functionalized with strong bases such as quaternary ammonium hydroxide, we are getting this resin, anion exchange resin, have the OH minus active anions. So we have on the cation exchange resins, active cations. On the anion exchange resin, we have active anions. Now, these resins with active cation, active anion can be used for cations exchange from the mineral salts and anion exchange from the same mineral salts. So, this is the process, the block diagram of ion exchange process. The water is sent through the method. And here we have cation exchange column, where cations present in raw water, that is hardness causing salts, may contain calcium and magnesium. The calcium magnesium ions are exchanged in cation exchange column. The process would be, let us say, resin with H plus is RH plus the hardness causing salts have active cations such as calcium or magnesium, can be converted into R2Ca or R2Mg. So this is cation exchange resin. Calcium or magnesium ions present in hard water, hardness causing salts present in water. Now what happened when you treat this raw water? When we send this raw water to this cation exchange column, RH plus, the H plus is moving to the water, calcium or magnesium ions moving towards the resin. We call this as exchange. The exchange of cations took place to form the products R2Ca, means calcium magnesium ions, went to resin, then H plus ions are coming into the water. So this is the ion exchange process happening in cation exchange resin. Similar process, after the water is flowing through cation exchange column, this is moving towards anion exchange column. So here also what we call, we have the resin with active anions. Now the anions will be exchanged with anions present in the water. the water containing hardness causing salts. The hardness causing salts containing anions are chlorides, sulfates, nitrates, etc. So the similar process as in case of cation exchange, here also we can see anions are exchanged with the resin. Chlorides, sulfates and nitrates move to the resin, OH minus move into the water. This is anion exchange resin. This is hardness causing salts containing anions present in water. So what would be the product here? RCl, RR, NO3 or R2SO4. So after exchange of anions with respect to water and resin, these would be the products. Our all anions move towards resin and resin having OH minus moving towards water. So now we have, after cation exchange process, H plus is moving to water. After anion exchange process, OH minus ions are present in water. Now this H plus and OH minus again form water molecules. So this would be the process for cation exchange and anion exchange in the technology. So after continuous removal of hardness causing salts in the water, these resins may get exhausted. These resins may become exhausted. Exhausted means they cannot exchange the cations or anions further. They become completed. All the R is with the complete calcium magnesium, or R is with complete Cl minus NO3 or SO4 minus 2. So there would be no RH plus and no ROH minus to further purify the water. So now we need not to discard this resin even though they are exhausted. So here we have the other components in the technology, dilute HCl and dilute NaOH. So this dilute HCl is used to regenerate cation exhausted resin. Regeneration for cation exchange resin. So our resin is with R2Ca or R2Mg. This we call as exhausted cation exchange resin. Now this is treated with dilute HCl. What we need? We need RH plus. We are getting this RH plus again, so that our exhausted cation exchange resin regenerated. Once we regenerate this resin, again the process continues. Similarly, exhausted anion exchange resin, what we had on the exhausted anion exchange resin? RCl, RNO3, R2SO4. So this is exhausted anion exchange resin. Now to regenerate this anion exchange resin, we need dilute NaOH, so that you get again regenerated anion exchange resin. NaOH, strong base but in dilute condition. Here also we are using strong acid but in dilute condition. We are going to get regenerated cation exchange resin, regenerated anion exchange resin. So again the process continues. Now our cation exchange column contains regenerated cation exchange resin. Anion exchange column contains regenerated anion exchange resin. What happens further again, as we discussed earlier, how the ion exchange process happens with RH plus, ROH minus, exchange of cations, exchange of anions takes place continuously, and then we get from this process, the significance of this process, the efficiency of this process is, if you send the raw water around 500 to 1000 ppm hardness, the raw water if contains 500 to 1000 ppm of hardness also, this technology treats the water, and the demineralized water, deionized water, what we are getting out of this technology contains approximately 2 ppm of hardness only. See, from 500 to 1000 ppm, The water now contains only 2 ppm of hardness causing salts. Now this is, again we have one more clarification here to explain this cation and anion exchange process. This is anion exchanger. This is anion exchanger, let us say, that is ROH minus having negative charge. So what happens? Negative charge is having, this is ROH minus, this is cation exchanger RH plus. So this is attracting all negative charges, that is chloride, sulfates and nitrates. This resin has H plus ions, so there will be exchange, replacement, substitution kind of reactions takes place. H plus is substituted with calcium or magnesium, OH minus is substituted with chloride, sulfates or nitrates. So this is how we can treat the water which has around 1000 ppm of hardness to 2 ppm of hardness. Again, this method is highly effective, having the sustainability. As you are going to regenerate this, we can reuse this process using dilute HCl and dilute NaOH. You need not to discard these exchange resins. You can regenerate the process again and again. Considering the sustainability and circular economy principles, we can consider this method as sustainable. Thank you.